Look at your hand for a moment. Every cell in your body, the device you are holding, and every glowing star in that distant galaxy represent a tiny minority of our universe. All the physical stuff we can see and touch makes up only 4.6% of reality. The rest is a mystery of invisible dark matter and dark energy. We call this visible sliver ordinary matter. It is defined by two simple traits. It has mass, the amount of physical material packed inside, and it has volume, meaning it occupies three-dimensional space. If you can weigh it and it takes up room, it is matter. This is why a beam of light or the heat from a flame are not matter. They have no mass and do not take up space. At the atomic level, matter is mostly empty space. You don't fall through your chair because of a rule called the Pauli exclusion principle. The particles that make up you and the chair are forced to maintain a strict distance from one another. This quantum social distancing prevents atoms from overlapping, which is what makes solid objects feel solid. By identifying the basic rules of this 4.6%, we can begin to see how the visible universe organizes itself into the complex structures we see every day. Matter changes its behavior based on its energy level. By adding or removing thermal energy, what we feel as heat, we can shift how these particles interact. These energy shifts create the states of matter. In a solid, particles are locked in a grid, just vibrating. As we add heat, they become a liquid, gaining energy to flow. With more heat, it becomes a gas, flying at high speeds. These neon signs contain the fourth state of matter, plasma. When a gas is hit with extreme heat or electricity, the energy becomes so violent that electrons are stripped away from their atoms. This creates a massive, glowing, electrified cloud of charged particles that behaves very differently from a normal gas. Transitions like melting or boiling change the movement of the particles, but the substance itself remains the same. Whether it is ice or steam, the speed of the dance is what defines the state. When you melt chocolate, it turns to liquid, but it can be cooled back into its original solid form. This is a physical, reversible change. However, when you fry an egg, the heat permanently alters the proteins. Because the internal bonds have changed, you can never turn a fried egg back into a raw one. When different elements undergo a chemical change to bond together, they form a compound. A compound is like a baked cake. The original ingredients have been chemically locked together to create a substance with entirely new properties. Water is a perfect example. It is made of hydrogen, an explosive gas, and oxygen, a gas that fuels fire. Yet when they bond, they create a liquid we use to put out fires. The compound behaves nothing like the elements that built it. Contrast that with a mixture, like a bowl of salad. The ingredients occupy the same space, but they never chemically bond. A tomato in a salad is still a tomato, retaining its own identity and properties. Because mixtures are held together by physical contact rather than chemical bonds, we can use physical methods to separate the ingredients and recover them. Chemists isolate pure substances by exploiting differences in their physical traits, such as their boiling points, densities, or how well they dissolve. Fractional distillation is used to separate liquids that are dissolved in one another. By slowly heating the mixture, the liquid with the lowest boiling point turns into a vapor first, allowing it to be captured and cooled back into a pure liquid. These industrial towers use this process to refine crude oil. As oil vapors rise, different fuels like gasoline and diesel cool and separate at different heights, allowing us to harvest them individually. We can also separate similar substances using paper chromatography. As a liquid solvent climbs up a piece of paper, it carries a mixture with it. Some compounds move quickly through the paper fibers, while others lag behind, separating the mixture into distinct spots. By dividing the distance a spot moved by the total distance the solvent moved, we calculate the RF value. This mathematical ratio serves as a unique fingerprint, allowing labs to identify specific ingredients in foods or medicines. Whether we are refining fuel or identifying a dye, these techniques allow us to isolate and control the individual components of matter. The periodic table organizes every known element in the universe into a grid that predicts how they will react and bond. In 1869, Dmitry Mendeleev noticed that when elements were arranged by mass, their chemical properties repeated in predictable intervals. He was so certain of this pattern that he left gaps in his table, describing the properties of elements that hadn't been discovered yet. When they were eventually found, they matched his descriptions perfectly. This organization reveals visual trends, like atomic radius. As we move from left to right across a row, we add more positive protons to the nucleus. This stronger pull drags the negative electron cloud inward, meaning atoms actually get smaller as you move across the table. The periodic table demonstrates that the behavior of matter isn't random. It follows a predictable map governed by atomic structure. At the bottom of this table, the heaviest elements reveal a secret. The laws of chemistry are affected by Albert Einstein's theory of relativity. In massive atoms, the highly positive nucleus pulls the innermost electrons so strongly that they travel at nearly the speed of light. At these speeds, the electrons gain mass, causing their orbits to contract toward the center. This relativistic contraction is why gold has a warm yellow color, and why Mercury refuses to solidify at room temperature. Mercury's outer electrons are held so tightly to the nucleus that the atoms cannot bond with one another, keeping the metal in a liquid state. From the way atoms occupy space to the relativistic speeds of electrons, the universe follows a consistent and understandable set of rules. When we look at ordinary matter, we aren't just seeing stuff, we are seeing the results of a masterful physical design.